Okay, so it's time. So welcome everyone after the break, and it is my pleasure to have Alessandro Monguzzi from University of Bergamo, and he will be talking about the Drury Arveson space on the Siegel upper half space and a von Neumann inequality. So please, you can start.
Okay, so thank you. So thank the organizer for the opportunity to give a talk here in this in this workshop, in this week of this focus program. And thank you the audience to be here. So as you can see, I will talk about the Drury Arveson space, which is the main character of this week, but not in the classical setting of the unit pole, but in the setting of the Siegel upper half space. And I will talk about the von Neumann type inequality in this setting. And I will try to motivate a little bit, at least, why I think it is nice or useful to have also the Drury Arveson space in this setting. So the work I will talk about is a joint work with Nicola Arcozzi, Nico Salmoukis, Marco Peloso, and Maura Salvatori. So I will spend the first minutes to actually recall a little bit of basic facts that I'm sure we all know about, but I will do it anyway, just to have a common notation and a common setting. Okay, so H will be a reproducing kernel in the space. So I have a space of functional domain omega, and the point evaluation is bounded. So I have a reproducing kernel Kz in H such that f of z is a f inner product Kz for all f in H. Then let us consider B, D plus 1 is the unit ball in CD plus 1. So here I want to point out the fact that my dimension is D plus 1, and it will be clear later why I use this dimension D plus 1. And so in particular, the case D equals 0 is actually the one-dimensional case, the complex plane. And as we actually already saw this morning with Mikkel lecture, we can consider on the unit well for a given parameter nu greater than -d minus 2, this well-known family of reproducing kernels. Okay, so this family includes Bergman spaces, Wedbar Bergman spaces, all spaces that we all know about. So we have the Hardy space on the unit ball for nu equals -1, the Bergman spaces for nu equals 0. When nu goes to -d minus 2, we actually have the limit case, which is the Dirichlet space, and the kernel look a little bit different. We have a logarithm, and for nu equal -d minus 1, we have the Drury Arveson space. So here I ask you for forgiveness because I'm using this non-standard notation. I apologize, but we started using this notation with my collaborators, and we add a lot of H in the paper. We also for the Heisenberg group and stuff like that, and so we use this non-standard notation, and I hope it will not confuse you. So this is the kernel of the Drury Arveson space. So as we saw this morning in Mikkel lecture, this is the norm of a Drury Arveson function. If we f as this power series expansion, and this is the norm. And as actually Mikkel also mentioned, we do have also an exact integral representation for this norm. This is just a curiosity, but I will show it to you anyway. Because if we have R to be the radial derivative, which is defined like this, and we set this, we introduce this differential operator. Script R0 is the identity, and we define script Rk to be the identity plus the radial derivative over k of script Rk minus 1. Then if you consider this differential operator, you actually have this identity. You have that the norm of the square of the norm of the Drury Arveson normal function f is equal to a dimensional constant, and here you have the L2 norm of this script Rd derivative of f, let's say, with respect to this weight here. Okay, this is an identity, it's not hard to check it, and okay. Actually, these differential operators were introduced by Marco Peloso in his PhD thesis in 1992, but you can also take a look at the recent paper by Arcozzi, myself, Peloso, and Salvatore. So now, let me now recall you the von Neumann inequality. So if H is an Hilbert space and T is a contraction from H to H, then we know that for any polynomial Pz, then the operator norm of Pt is controlled by the multiplier operator or the associated to the polynomial P as a multiplier operator on the Hardy space, which coincides with the L infinity norm of P. And then we know that this result has been generalized by Drury in what it is now the Drury Arveson space. So we have now a vector of D plus 1 operator, T1, TD plus 1 of linear operators on the Hilbert space H, such that they all commute with each other and they are a row contraction, meaning that this identity holds. Okay, this inequality holds. And now we know that if P is a complex polynomial in Z1 ZD plus 1 variable, then the norm of PT is controlled by the norm of the multiplier operator associated to P as a multiplier acting on the Drury Arveson space. So what I will do in the next minute is to give a kind of this result of this kind in the setting of the Siegel per space. Okay, so what is the Siegel per space or Siegel space? Is this following domain in CD plus 1? Is the domain given by the pair ZD plus 1 in CD. So this Z is in CD times C. So that's basically the reason why my dimension is CD plus 1, such that the imaginary part of ZD plus 1 is greater than 1 over 4, which is just a dimensional constant, a normalization constant, the mod square of Z. So I use the dimension CD plus 1 because, as you can see, the last direction, the last component, ZD plus 1, as let's say a special role, as is different than the first D direction. Then I also introduced these coordinates that actually I will not really use, but these are called the Heisenberg coordinates, and it will be clear later why, that we can describe this domain as follows, as the point Z, T plus I over 4Z squared plus IH, so that Z is in CD. So the Latin Z and the Greek Z actually is just a different notation. T is the real part of ZD plus 1. And for the imaginary part, we write I over 4 mod square of Z plus IH. So if H is equal 0, then we are on the boundary of the domain. If H is positive, we are in the interior, in the domain. So H is a sort of 8 over the boundary of the domain, let's say. And so in this setting as well, we can consider the analog family of reproducing kernel Hilbert spaces we saw on the unit ball, which is the family of reproducing kernel Hilbert spaces associated to this family of kernels. So the kernel look like this. Okay. And so we have omega D, okay, a constant which depends on D and nu, omega D plus 1 minus Z bar D plus 1 over 2I minus 1 over 4. And this is the Hermitian product in CD between omega and Z. So also in this setting, this family of spaces is not as known as in the unit ball, but for sure the most classical spaces are well known, such as the Hardy space, the Bergman space. We actually studied in my paper together with Arcozzi, Pelosi, and Salvatori a little bit of the Drury space in this setting and the Drury Arveson space in this setting, which corresponds also in this setting to the case nu equal minus D minus 1. Okay, so this is the kernel we are interested in. So how you obtain this kernel is quite easy. I mean, you obtain this family of kernel because at least if you consider the Bergman space, you can just use bialomorphism with the unit ball and you obtain via the standard transformation rule for the Bergman kernels, what is the candidate kernel, then you can study the whole family of kernels. So, okay, but why we consider the Siegel space? What's the point to consider this family of domain in this setting? So for one, first, okay, the Siegel space is a bialomorphic copy of the unit ball, but it is an unbounded bialomorphic copy of the unit ball. So for sure, on one end, you can obtain or at least understand what can happen on the half plane via bialomorphism with the unit ball, but not all the results actually can transfer trivially via bialomorphism. And from the theory of function, from the point of view of function theory, still it is an unbounded domain. So also, I mean, the function theory on the half plane and the function theory on the unit disk is not similar, but it's not completely the same. And the half space actually is somehow the Siegel half space is somehow the correct generalization of the half plane in several variables. Also, in the Siegel half space, what you do is actually somehow you break the symmetry of the ball. I mean, it is a bialomorphic to the unit ball via the Kelly transform, but you break the symmetry, meaning that we saw the definition, the ZT plus one direction is different than the others. I mean, it's a transversal direction to the boundary. And so this breaking the symmetry, not all the variables are the same now as in the unit ball. So this actually can help you to understand a little bit what's going on. And maybe you can use the point of view of the Siegel half plane to understand actually things on the unit ball. So to go the other way around. And also a very important thing is that the boundary of the Siegel half space can actually be identified with the Heisenberg group. And this is very important because this provides us a lot of tools from harmonic analysis on groups that allows us to study these spaces. Okay, this harmonic analysis on groups is very well developed, and we have a very flexible tools that can be used to study these spaces. And let's say that on the unit ball, you have a normomorphic function and you can study it, and you actually do study the spaces using the power series expansion of the function, which is somehow the analog of studying using the harmonic analysis here on the group. But maybe it's not that, sometimes the power series expansion is not that flexible, let's say. And also the Siegel half space, okay, is bialomorphic to the unit ball, so you can understand it's a good starting point to actually generalize to more general domains, which are called homogeneous Siegel domains. And here I only recall some recent work by Calzi and Peloso, and they have a lot of references in their work, so I refer you to take a look at the reference in their paper. So this is a motivation, I mean, of why I think it is worth to study these spaces in this set. So let's take a look at a function theoretic description of the Drury-Arveson space on the Siegel half space. So let be rho of z, zd plus 1, this the defining function of the domain. So the imaginary part of zd plus 1 minus 1 over 4 mod square of z. And then f, now a function f is in the Drury-Arveson space if two things hold. We have that here we consider the derivative of order from j that goes from 0 to d minus 1, and we derive with respect to the last variable, and we have this weight here, where this weight here is just the defining function, and we require this limit to be 0 when the imaginary part of zd plus 1 goes to infinity. And the norm is given by this quantity here. We are integrating the d derivative with respect to the last variable is an L2 norm, and here we have this weight here and this weight here. I could have put them this way together, sorry. And so you can think of this as, we actually saw this morning with Michael, where here you had in the unit ball, you had the radial derivative, and here instead of this rho function here, you have 1 minus mod of z squared, okay? So this is kind of the Bezos-Sobolev description of the norm from the Drury-Arveson space. Okay, so this is our domain. This is the kernel of our space. And let us now introduce the operators we are dealing with. So we define a vector of operator A1, AD plus 1 to be a Siegel dissipative vector of kinetic operators on an Hilbert space H. And we require the following. We ask for the first D operators A1, AD to be bounded. We require the last operator to be closed, densely defined, and we ask the resolvent of I AD plus 1 to contain the positive half line. We require the first D operators to commute with each other and to strongly commute with the last operator. So the last operator is not required to be bounded, so we need a definition of commutativity between a notion of commutativity between the last operator and the first D operators. And finally, I have this requirement of dissipativity, let's say. So we require the imaginary part of the inner product of AD plus 1V inner product V to be greater or equal 1 over 4, and this sum here. So as you can imagine, of course, this condition is modeled on the kernel of our space. In particular, I want to stress out the fact that by the Lummer-Phillips theorem, and this condition, the condition 2, condition 4, we actually have that IAD plus 1 is the infinitesimal generator of semigroup of contraction. And all these contraction, they all commute with the first A operator AJ with J that goes from 1 to D. Okay, so this is our set. And this is the theorem we prove that given such a vector of operators, and let us consider for any tau J, negative tau J, for J that goes from 1 to D, we consider the operator Mj, which is defined in this way. So e to the minus I tau J AD plus 1 AJ. So is the composition of one of the contraction of the semigroup generated by I AD plus 1 with AJ. And we consider the analog function in ZD plus 1 ZD. Okay, so E minus I tau J ZD plus 1 ZJ. And then we have that for any complex polynomial of D variable, not D plus 1, this is not a type of D variable, we have that the norm of the polynomial in the big M1 MD variable, so we have a polynomial in these operators here, is controlled by the norm of the polynomial of the polynomial P in the variable little m1 little md, and this is the norm of the multiplier operator associated to this polynomial, let's say, on acting on the Drury Arveson space on the Siegel space. So I want to point out a thing here that we do actually need to this tau j to be negative, strictly negative, because if not, this function here are turn out to be they are not multiplier for the Drury Arveson space. If tau j is 0, this is no longer a multiplier. So what I'm saying is that the multiplication by a coordinate is not a bounded operator in our setting. And this is an effect, meaning that there is a paper by Ambrosi, Englis, and Muller for about von Neumann inequalities in general setting in CN, but they do require in their spaces as an axiomat, they define some spaces axiomatically, and they do require the multiplication by coordinates to be a bounded operator. And this is not the case for us. And it is in the nature of the space we are considering. So now we'll spend a little bit about the proof of this theorem. And okay, how to prove this theorem? Actually, if at least you assume all the operators to be bounded, you can surely obtain a proof of this theorem by using the Cayley transform and the biholomorphicity with the unit ball and the classical inequality on the unit ball. And this was actually pointed us out by Michael Arts, but what we do is we prefer to follow a direct approach because, and actually following in the step of Drury's original proof, because in doing so, we actually develop a little bit of machinery in this setting that we think can be useful or interesting in its own, and maybe can be useful, to study. Now we have these multiplier operators arise naturally, so maybe it would be interesting to study in this setting invariant subspaces with respect to these multiplier operators or stuff like that. So the proof is based on the following fact that this diagram commutes. And so now I will try to tell you a little bit what are the objects in this diagram. Okay, so here, this is the given Hilbert space, and this actually is a multi-index notation. A to the gamma is E1 to the gamma 1, E2 to the gamma 2, and so on till ED to the gamma D. And this is a bounded operator, and this is immediately follows from the definition of the Siegel dissipative vector of commuting operators that we used. Now, we have this L2 space. What is this L2 space? So d mu, so here we are living on ND, so the D product of, and so this is the product of D copies of the natural numbers times the negative real line. And we have this measure d mu, which is some weighted measure. Here you can read the weight. Maybe it will tell you, it won't tell you anything, I think, but here I'm just saying that d alpha is the counting measure on ND and d lambda is the Lebesgue measure on the negative real line. So what is this space? Why would we have this measure and why we have this L2 space? Okay, this space is just a copy of the Drury-Arveson spaces, meaning that we have a map from this L2 space into the A, which is a surjective isometry. And the map as looks explicitly like this. I think it will not tell you much because it's quite a complicated formula if you read it for the first time. But what I want to point out is that this is a more precise formulation of the Peli-Linear theorem for the A, meaning this is nothing more than the inverse Fourier function on the Heisenberg group for a given function on the Drury-Arveson space. Okay, because I recall you that the boundary of our domain can be identified with the Heisenberg group. And if you use the Heisenberg coordinates ZTH that I introduced before, that maybe you already forgot about them, but we have some special coordinates that somehow reflect the geometry of the group and of the domain. And you have this formula here, which maybe is new for you, maybe not, but it's just the inverse Fourier transform on the Heisenberg group. So this is a well-known object. And this is the planchard formula that you have the Drury Arveson norm of F is given by the L2 norm of the Fourier transform. So the Fourier transform of the group of a function F is a family of operator sigma lambda F. Sigma lambda F is a family of Hilbert-Schmidt operator, and we have this planchard formula. So here I don't want to go into details because they are too complicated, but I want just to, the takeaway message is we have the Fourier transform on the boundary, and this L2 spaces is the image of the Drury Arveson space via the Fourier transform of the boundary value of the function in our Drury Arveson space. And we use the fact that boundary of the Siegel space is the Heisenberg group. Okay, so here we use the harmonic analysis on the group. And then, of course, we know now why we have this L2 space, and now we consider H valued function. So here we go from G to the domain of the last operator AD plus 1, and we consider a new norm here, where this delta norm is the following one. So here we are really somehow we are in the step of Drury's original proof on the unit ball. Okay, and so here is where our dissipative condition on the operators plays a role. Okay, so now, okay, I told you what are all these objects. Now theta, as you can imagine, is an isometric embedding from our space to this L2 space. And so here is the isometric embedding explicitly given. We do have this isometric embedding. And finally, we have this last operator here, which is a star tensor of identity is a shift. If we have gamma in ND and a negative tau, then S gamma tau phi is this weighted shift operator. And it is a bounded operator in L2, and it is unitarily equivalent to the multiplier operator on the Drury Arveson space with this multiplier here. So we have the exponential in the last component and the multiplication by the first D coordinates. Okay, and then S star is the adjoint. We have this is the explicit expression. Okay, the formula are complicated to read, but this is a weighted shift operator. Okay, which is unitarily equivalent to this multiplier operator on our Drury Arveson space. And then we tensor with identity. Okay, so so here now we are done. I told you everything, and just to recap, is H is the Hilbert space, and A1, AD plus 1 are the given operators. So this L2 space is for us just the Fourier transform of our Drury Arveson space. This operator here is well defined and bounded because of our assumption. This weighted shift operator is the Fourier transform of the multiplier operator associated to this multiplier, and theta is an isometric bearing. So we can represent any such operator which arise from a Siegel dissipative vector of a commutative operators as a weighted shift operator on this L2 space. Okay, and now the proof follows, because as you can imagine, this is now the the inequality we want to prove. Now let us forget about the sum, just prove it for only one term. So we have the Hilbert norm, the H norm of this object here. We use the isometric embedding, and then we use the fact that our commutative diagram, okay, and so on. So here now we have the weighted shift theta, and then we use the boundedness, the isometric embedding theta, the boundedness of the weighted shift, and the fact that the weighted shift is unitarily equivalent to our multiplier on the Drury Arveson space, and the conclusion follows. So what's the takeaway message? This is a new point of view, maybe not new, I think, point of view on a well-known space. Maybe can be useful to study this some problems in this setting that can maybe it will hopefully it will be useful to have this point of view and will answer to some problem on the unit board or the other way around. And so this is it. I think my time is over. So thank you for your attention.
Okay, so thank you very much for this talk. So is there any question or comments?
I have a question, two questions. The first one is, what is your demu?
Demu is, sorry, is this weighted measure here. Where is it? Is this weighted measure here?
Okay, thank you. And the second one is, do we know the zero set of the DA space?
So sorry?
Do we know the zero set of the DA space?
Of the Drury Arveson space?
Yeah. Because in fact, with your Pauli-Wiener theorem,
yeah,
we can do a kind of maybe Mons type theorem on L2, on your L2 space.
Yeah, I see what you're saying. I don't think I mean, I do not know actually. I don't think we have a description of the zero set of the Drury Arveson space in this setting. I don't know. Okay. At least I don't know it.
Thank you.
Thank you for your question. Sorry not to be helpful, but thank you. So, okay.
So, is there any other question for Alessandro?
Yes, Alessandro, is for the half space. Is the Shiloh boundary the same as the topological boundary?
Okay, is the Shiloh boundary as the same as the topological boundary in for the Shiloh here? I think that here in the Siegel space they do coincide. If you consider more general homogeneous Siegel domain, then you have a difference, the Siegel bound in the Shiloh boundary and the topological boundary. But in my setting here, I think this is the same as the Shiloh boundary. So the Shiloh boundary and topological boundary here, they coincide. Thank you for the question.
Okay, so is there any other question for Alessandro? If not, let's thank the speaker again.
Thank you.